Okay, so let's restart. Okay, so let me come back to some points here. So some people have come up to me and have asked, really good questions. So this equation, where does it come from? It's like, okay, you maximize the expected return minus the cost of risk. So it looks kind of like a little bit like a black box. So it looks like a little bit unclear. So why not like decompose it and make it clear into various parts. And so basically, this equation, it's like, okay, so uh, who makes this decision of capital structure? Okay, so it depends. Somebody could be making this decision. So, for example, in this example, so the households, they have some capital with idiosyncratic risk, and this idiosyncratic risk they can insure by passing it to intermediaries, and the intermediaries, they do something to insure it, and then there is a price for insuring this risk. So basically, this part is the price for insuring this risk through intermediaries, because the intermediaries, they will require this risk premium for insuring this risk, and this is the cost of holding risk, uninsured by the households, and basically the household will choose how much risk to insure and how much to hold, basically to minimize this. So basically, this is what is the happening here. Somebody is making this decision, and basically, if you wanted, you could basically look inside this black box and look into it in more detail. So you can look at, okay, how this risk is divided, and as a function of how this risk is divided, how the return of the assets divided between the different stakeholders. So maybe the managers, maybe they're holding concentrated risk in the inside equity, so they maybe get a higher fraction of the return, and outside equity holders, they maybe get a little bit less, and debt holders, they get, even a little bit less. So you can look at, how those returns are divided, and then you can look at, all of the balance sheets of individual agents and basically break them down and see how much people earn on different parts of their balance sheet. And this is what I used to do. And it's a lot of algebra. It's like, if you keep track of all of those components, it's like a huge mess. It's like, takes a very, very long time to plow through, okay? And after a lot of suffering, what I have realized is that suffering can be avoided by writing it this way and basically focusing on what's essential, okay? And what is essential here is that you get a choice that of capital structure that basically maximizes this objective, and out of this equation, what you get is you basically get the output, and you also get the allocation of risk between the stakeholders. So basically, each agent group with a different risk premium, how much risk do they get, and then you get the allocation of risk. Okay, and the allocation of risk is all you need to know in order to get the law of motion of the wealth distribution. Okay, so when you write things in terms of risk premia, I mean, of course, what matters for the law of motion of the wealth distribution is the whole allocation of assets, but a sufficient statistic is the allocation of risk, and so I'm going to show in a moment how to derive the wealth distribution from the allocation of risk. So basically, it's like, okay, you can solve for the, you can basically derive all of these cash flows, okay, but you do not need to know all of those cash flows in order to solve the model. So you can solve the model just by focusing on the risk and the risk premium. You can derive the cash flows later. Okay, and then one of the questions you may ask is like, what is this equation connected to? And so let me come back to this equation, which is the key equation from optimal consumption and portfolio choice calculations. Okay, and suppose that asset B is the risk-free asset, and asset A is some risky asset. Okay, then if I plug in the risk-free rate, and if I plug in for the risk-free asset 0, then I get something like this, right? So basically I get this equation that this is the risk premium of asset A over the risk-free rate is explained by the risk of asset A times the risk premium. Okay, and this is just asset pricing. Okay, but this equation is that your return and your risk of the asset depend on some choices, in particular the choice of capital structure. And that choice of capital structure is going to determine how you divide the risk among the different stakeholders. So then if you choose this capital structure, your expected return is going to be a function of your choice of the capital structure. And the risk is also going to be a function. And this is actually a vector of that determines how the risk is divided between the different stakeholders. This is a vector of risk premium. This is a vector, right? And basically, this condition is that condition. So in equilibrium, it has to hold with equality. If the agent within that firm that makes this capital structure decision and makes this decision how to sell the different stakes, if that person makes the decisions optimally, then basically they get the required return. But and in equilibrium, in a competitive equilibrium, all of the decisions are made optimally, and you get and basically you get the required return from all assets. And of course here, if you make this decision for this firm, you're a price taker. So you take the vector of market risk premium as given. Whereas if you thought about the planner, then maybe the planner would think about how these decisions, how they affect the allocation of risk and how they feed into the risk premium. Then you could also maybe look at that. Okay. So, all right. Okay. So this is the allocation of assets, and let me box this equation. This part. And given this allocation of assets, you get some allocation of risk. So, for example, here, what is going to be the for example, in this model, what is going to be the risk of experts' wealth? So the risk that the experts face is psi over eta times sigma plus sigma q. This is sigma n. This is the risk of experts' wealth. And if I want to get the risk of eta, which is the ratio of n to q times k, then I have to take this risk of n and I have to subtract the risk of q times k, because whenever we have a ratio, then the risk of the ratio is the difference in volatilities. And so because of that, the risk of experts' wealth share equals psi over eta sigma plus sigma q minus sigma q. This is the volatility of q times k. Okay, so now imagine some type of a model, and suppose that so this is our canvas. This is the state space. Okay, and I plot on the vertical axis the risk exposure of experts. Okay, so this is, for example, the volatility of experts' wealth, and I plot the risk exposure of households. Okay. Okay, so this is a picture that if you know the allocation of capital, so if you solve for the allocation of capital, or if you solve for the allocation of equity shares, and if you know the risk of capital, then basically you can derive the risk. So here, this is the volatility of eta, and given this specific solution, it's going to be A minus A underlined divided by sigma times 1 minus eta. This is sigma eta in this case. So it's going to be the minimum minimum of this expression, and if x holds all of the capital, then 1 minus eta over eta sigma, the minimum of these two expressions. Okay. So you can tell me that, well, if we have the allocation of risk, then basically we know the volatility of the wealth shares. Okay. And one of the questions you may ask me is that, well, what about the drift of the wealth share? So can we derive from the allocation of risk what are going to be the risk premia and what is going to be the whole law of motion of the wealth distribution? And it turns out that there is a way to do it, and there's a very, very nice and clean way to do it. So let me basically show you the best way to do it. So what I'm going to do is I'm going to do it a little bit more generally than I've been doing things so far, because so far I think in all of the examples there are only two types of agents. Okay, so let me imagine that there are n types of agents, so I equals to 1 to n. Okay, and so there could be households, there could be entrepreneurs, there could be one type of intermediaries, another type of intermediaries. So you could have basically a whole system of intermediation, and eta I. This is the wealth share of type I. Type agent I. So these wealth shares, they add up to 1. And let's imagine that these agents, that they're going to have some, so this is the volatility of wealth share of agent of type I. Okay. And if I take a weighted average of these with those weights, then the weighted average is going to be 0. Because the weighted average is going to be just the volatility of 1. The whole wealth share is 1. Therefore, and 1 is a constant, has volatility 0. Okay. So, and because we already had one example with this idiosyncratic risk, I'm going to make this even more general. I'm basically going to allow for agents of type I to also be exposed to some idiosyncratic risk, and this is the idiosyncratic volatility of wealth of agents in group I. Okay, so basically, what this is that in this example, sigma tilde h is equal to we have risk 1 minus psi, is their wealth share, and this is how much risk that they're exposed to. So basically, this is going to be the idiosyncratic volatility of their wealth. Okay, so if you figure out the right way to look at it, you can do it really, really quickly. And what does it mean to figure out the right way of doing it? That means, so what I'm going to do is I'm going to basically use this asset pricing equation to get the drift of wealth shares from the distribution of risk. Okay, and why is it that I can do it? Well, you can sort of see why it is that I can do it is because if you have the allocation of risk, then you can basically derive a risk premium from the asset pricing equations, and then you can combine those risk premium, and then you can basically get the drift of wealth of everybody. You can combine it together. You can get the drifts of wealth shares, right? But in fact, you can derive the law of motion of the wealth distribution very fast if you apply this asset pricing equation to the right type of an asset and in the right numerator. Okay, so so the question is, what is going to be this asset, and what is going to be the numerator that's convenient to use to derive the law of motion of wealth shares. So asset and numerator. Okay. So so if you choose those correctly, you can derive this equation very, very quickly. And for the asset, I'm sort of thinking because maybe I can do it even more efficiently. but okay. But let me not worry about it. So for the asset, let's do the whole portfolio of agent I. So I'm not going to price the individual assets in agent's I portfolio, but I can apply the asset pricing condition to the whole portfolio. And why is it that I can do is that because, well, this has to be a martingale for any trading strategy. Well, for any self-financing trading strategy. So basically, I'm going to look at the whole portfolio of agent I. And for the numerator, what I'm going to use is I'm going to use world wealth as the numerator. Okay. And why this is convenient? Because if I use so what is the wealth of this group I in this numerator? Is that, well, their wealth in this numerator is just their wealth share, right? Because it's their wealth relative to the whole. So basically, in this numerator, their wealth is eta I. Okay, their wealth is eta I. Okay, and now I'm going to apply the asset pricing equation to this their whole wealth portfolio. Okay, so in order to apply this asset pricing equation, well, okay, so what is the risk of the what is the risk? So the risk is sigma eta I dz. So they have this aggregate risk plus individual agents. If you want to also add the idiosyncratic risk, then they also have the individual agents in this group. They have this idiosyncratic risk and this common risk. And if you don't want to worry about the idiosyncratic risk, you can put it to 0. But basically, this is going to be the risk, and the return is going to consist of a capital gains rate and dividend yield. So the dividend yield is just so the dividend is how much they consume divided by their wealth. And this whole equation gives us the return of entire portfolio of agents in group I. And this is kind of weird, right? Because of the numerator that we use, right? But basically, the capital gains rate is just the drift of their wealth share. The dividend yield is their consumption rate, and this is the risk is just the risk of their wealth share, because you look at the risk, not the total risk, but the risk in this numerator. So we're looking at the risk of their wealth share, and plus there's some idiosyncratic risk, and the idiosyncratic risk does not depend on the numerator. Okay, and so to apply this equation, you need asset A and asset B. Okay, and for asset B, we have to be a little bit careful. So suppose asset B. So I'm going to apply this equation for agent type A, and so for agent type I. And asset A is basically going to be this whole portfolio. So this is something that agent type I is going to hold. And asset B is going to be an asset which everybody can hold. So for example, the risk-free asset. But basically, both assets, they have to be both assets that can be held by agent I. So this is asset A. And the asset B, let's say it's the risk, for example, risk-free asset. And why I say say, for example, is because Marcus and I, we are also interested in money, and so we are interested in models where money is not a risk-free asset, but there's monetary authority which could affect money return through monetary policy. There could be inflation sometimes, and so risk-free asset is just one example, but could be another asset. Okay, but here one has to be careful because if the numerator is world wealth, then in terms of world wealth, the risk-free asset is not risk-free. So in terms of maybe it's risk-free in terms of consumption, so it's risk-free. But in terms of so I'm not going to write it as a risk-free asset because of the change in numerator. So I'm just going to write it RM, some return on money plus so this is the return on risk-free asset or money. Okay, so purpose will use the superscript M in world wealth as numerator. Okay. And all right, so I haven't written any equations yet. All I've done is basically I just set some things up. Okay. So let me write down the equations. Here you can still see, or this is getting low. People in the back have trouble. But here you can see, right? Here it's a little bit higher, so let me use this slide. Okay. So let me write down this pricing condition. So I have the return on the whole wealth portfolio minus the expected return on money. Okay. This is for agent type I, equals the difference in risk. So sigma eta I minus sigma M. Okay, times the risk premium of agent I, and if you also want to have idiosyncratic risk, then I have to add the idiosyncratic risk of agent I, and then the risk premium for idiosyncratic risk is always gamma times. Yeah, this is the idiosyncratic risk. It's gamma times gamma times sigma tilde I. We also have idiosyncratic risk. So basically, you have this equation, and this equation is really cool. Okay, because what you want to derive is you want to derive the drift of the wealth shares, and this equation exactly gives you the drift of the wealth share of agent I. Okay. And you're looking at me skeptical, and I think the reason you're looking at me skeptical is because you're looking at this term here, which is the drift of the risk-free rate, and you can ask, well, what is that? Because we haven't derived the risk-free rate, especially not just the risk-free rate, but the risk-free rate in this funky numerator. What is the risk-free rate in this funky numerator? Okay, so so let me do something, and let me try to express this risk-free rate in terms of other terms. Okay. So the next thing that I'm going to do is let me take this equation and let me add it up across all agent types. Take the weighted average and guess with what weights. So of course with the wealth share weights, right? Okay, so basically add with weights eta I. Okay, so then all right. So if I add these things up, okay, let me explain a couple of things that happen. So one of the things that happens is that the weighted average sum of the drifts is 0, okay, right? Because the total adds up to 1. Okay, so the weighted average sum of the drifts is 0. So this is going to be 0. This part is going to be C bar over N bar, which is aggregate consumption divided by the aggregate wealth. Okay. The next part is Rm is going to remain Rm because the weights add up to 1. And then on the other side, I'm going to have sum over I of sigma eta I minus sigma m. So actually, let me add it over j, not to confuse it with that I. This is the risk premium j plus sigma tilde j squared. So this is, let's say, this is gamma I. They could have different risk aversion coefficients. Sum eta j gamma j sigma tilde j squared. Okay, and then so I got another equation, and this is, by the way, is going to be a useful equation. But then let me take this equation and subtract that equation. And here's what I get. So if I subtract it, then this Rm is going to cancel out, right? Because you didn't like it. So I said, okay, I'll get rid of it for you. So that I have mu eta I equals basically function of wealth share of agent I. Okay. And how to interpret it is that basically, well, if you get richer or poorer relative to others, it depends on two things. Okay, it depends on how much risk you take compared to how much risk others take, and it depends on how much you consume compared to how much others consume. So this is the average consumption to wealth ratio. This is your consumption to wealth ratio, and then this is your risk taking with your risk premium. This is your idiosyncratic risk taking, and this is the others risk taking, and this is the others idiosyncratic risk taking. So basically, this is what happens with this model dynamically. Okay. And you know what else is cool? I did not even use ethos formula to derive. I don't think I used ethos formula. Where did I use ethos formula? Huh? The asset pricing. Okay. So basically, I borrowed this standard material, but here I avoided using ethos formula. Well, you could tell me that I'm cheating because you could say, well, what is this sigma m? Like because in order to get this sigma m, I actually need to use ethos formula, right? So basically, so what is my sigma m? It's like, okay, where is my change of numerator equation? I basically take I normalize by this numerator, right? So the volatility in the numerator is the volatility before, which was 0 for the risk-free asset, and my numerator is world wealth. So basically, my sigma m is minus the volatility of world wealth. So sigma m for the risk-free asset. For the risk-free asset, sigma m is minus sigma n bar, volatility of world wealth with the minus sign. Okay, and so in that model, for example, this is equal to minus sigma plus sigma q. Okay. So let me take a step back, okay, and take a look and summarize some big picture connections. Okay, so so one fun fact about me is that back when I was in high school, I went to art school also. And so basically, I learned how to paint. And when you paint, sort of like you stand in front of your paintings and you paint because you cannot paint from far away. But it's very, very important that, and this is also important for economics, that you have to go back and you have to look at the whole picture, okay? And when you paint, you actually keep doing this. You paint something, you focus on small details, and then you go back and you look at it. You just keep doing it. And I think in economics, I myself at least, I forgot a little bit that I have to do, and sometimes, I stand too close, for too long, and I forget to. And I guess the further back you go, the more you see, right? So there are different perspectives, right? But going back and looking at the whole whiteboard, so one part is this asset allocation, okay? And some of you said that, well, this asset allocation equation is a bit like a black box, okay? And I say, okay, it's a bit like a black box, but it gives us the essentials. So what we get out of it is we basically get the allocation of risk. Okay, so we basically, well, we take these risk premia as given. Okay, let's take them as given. And given the risk premia, but if we have logarithmic utilities, then we have some specific form of the risk premium, so we can actually plug those in, right? But in any case, in general, we could take those as given, and we can figure out how this risk is allocated, and what output you're going to get. And you get this as a function of state space. And if you have the allocation of risk, then you can take it and you can plug it into this equation to get the dynamics for the wealth chart. Okay. And of course, here you also need the risk premia, but for log utility, you can figure out what those are. But if you have this part, so this is your state space. So basically, how you move through the state space. So basically, you have the risk exposures, and you have the volatility, and basically you move through the state space. And you know the different things that happen in the different parts of the state space. So where the fire sales happen, basically where risk is going to be allocated, inefficiently, and so basically then you get the whole big picture, how things are connected. And of course, at this point, you can tell me, well, but what about these risk premia, right? So where do they come from? So this is something I still need to address. So something else that I also need to address is, so this consumption ratio, where does it come from, right? This is something I still need to address. Okay, I'll address it. What else do we need to address? So, okay. All right. But I think I might have done it slightly wrong because, okay, of course I did it slightly wrong. Okay, because I mentioned earlier that the risk premium, you have to express them in the right numerator, right? And I think my original definition was that this is the risk premium in terms of consumption. Okay, so if I want to express the risk premium in terms of so to do it properly, I should actually express the risk premium in terms of world wealth, which means that I have to subtract the volatility of this deflator. So I have to subtract minus sigma n. I was told not to use this marker, so I'll use the black one. Sigma n bar. the reason I need it is because I'm about to use this equation. Okay. So let me use this equation for logarithmic utility. So for logarithmic utility, the risk premium is the volatility of wealth. So this is sigma ni, the volatility of wealth of agent type I. That's the risk premium. Kind of running out of whiteboards. Do you know if there are those, the big notepads? They exist somewhere in the department? I don't know. Do you think they exist, or do you think no? What we did in previous years is, we turned around and I wrote them. Okay, so success. Success. That would be good. Oh yeah. Okay. This will, because I can also flip it, so this will. Okay. Great. Wonderful. All right. So let me do it for logarithmic utility. So mu eta. This is, let's say, the drift of wealth share of let's say experts. And then I have in parentheses sigma eta, and remember that sigma n is okay. So maybe because this is not meant to be, this is not meant to teach anything. This is just meant to basically as an illustrative example, right? So let me make it simpler. Okay. So let me make it simpler. Let me basically consider this case that we have we are back in this case. We have a logarithmic utility, and we have basically no adjustment cost on Q is always equal to 1, so that the volatility of rolled wealth, sigma n bar, in this case, is equal to just sigma. So that's just for this specific case. Okay. So let me do it for this case because this is just meant to illustrate it. So I have sigma eta. Okay. And then I have minus sigma n, and sigma n is minus sigma n bar. So it's going to be plus sigma n bar, and sigma n bar is sigma, so it's going to be plus sigma. Okay, it's going to be plus sigma. Times I have sigma ni minus sigma n bar. Okay. So this is the volatility of the wealth of agent I, experts, minus the volatility of total wealth, and by Ito's formula, the difference of volatility is just the volatility of the ratio, and the ratio is the wealth share. So this in parentheses is just going to be sigma eta. So times sigma eta. Okay, and then I subtract this sum, right? I subtract this sum. And this sum has two elements because there are two agents, one for experts and one for households. So for experts, basically I subtract this times eta. So I have this times 1 minus eta. Okay. And for households, I subtract 1 minus eta. This is their wealth share weight times sigma, let's say, for the households, the household's wealth share plus sigma times sigma wealth share of the households, where this is the volatility of household wealth share, which equals minus eta times sigma eta divided by 1 minus eta. And we'll explain why in a moment. Because what we have is that, remember that these volatilities of everybody, if I add them up with weights equal to the wealth shares, the weighted sum equals 0. Okay? And the weighted sum of this one and this one with weights eta on this and weight 1 minus eta on that, that's what gives me 0. So that's why this is the volatility of wealth share of households. Okay. So let's imagine there is no idiosyncratic risk, so we do not worry about idiosyncratic risk, and then we just have minus the consumption over wealth of experts, so for log utility is just the discount rate, and then plus the average consumption rate of experts and households, so this is the weighted average of the discount rates of experts and households. So if this is the discount rate of households, this is the discount rate of experts, 1 minus eta. Basically, I have this equation, okay, and now you can see that if I plug this in there, right, then I can perform some cancellations. And if after I perform all of the cancellations, so this is the algebra that at this point it's just the algebra, and what you get is let me write it like this. Mu eta equals sigma eta squared plus times eta plus eta 1 minus eta. So basically this is the equation. Okay. So this is kind of neat and closed form. So basically, this is one example which illustrates that how if we have this is for logarithmic utility. If you have just aggregate risk, then this is a very nice and clean formula for the drift of the wealth share of experts. And by the way, if you did have adjustment costs, and if sigma n bar is not sigma but if it's sigma plus sigma q, okay. In that case, this formula is also valid, but you have to replace sigma by sigma plus sigma q. Okay, so basically you always get the same formula. Any questions? Yeah.
In the last equation on the left-hand side.
On the left, this one?
Yeah, that one.
Yeah.
In the sum, isn't there an eta j missing in the sum? Otherwise, I don't understand the next step. Over there, after the equal, there is a sum.
After the sum?
Yeah, that there shouldn't be an eta j weighting
these
terms.
Yeah. Yes. Sorry.
Okay,
yes.
then understand.
This is eta j, exactly.
Thank you.
Yeah, eta j. Yeah. Okay. So let me talk about something else, which I think is interesting. So let me talk about money. Okay. So one interesting question is, so people could be trading the risk-free asset in these models, or they could be trading money. So money. Let's think about money as basically as in Bewley economies. Okay, so basically, it's something that exists in this economy, let's say, in fixed supply, and it has no intrinsic value, but in equilibrium, it can have value because of some friction. And in Bewley economy, the friction is that the agents have this idiosyncratic risk, like here, which they cannot diversify. So basically, when people have idiosyncratic risk, this is the friction, and in the Bewley economy, people face idiosyncratic shock, and then they choose to basically something that is intrinsically worthless can have a value in this equilibrium. So let's imagine that basically people they use some form of money, and then you can think about money. Well, it's something that exists in fixed supply, and it cannot be controlled by any monetary authority. And later on, if you want, you can think about money as something that there's a monetary authority that can somehow conduct monetary policy. So basically, it can print some money, it can set the interest rate on money. But before going into monetary policy, that's just something you can do later. Let's think about money as something in fixed supply. Okay, and so So let's imagine a world like this. So basically, this is going to be an economy. This is the whole wealth in this economy, and let's say that theta of all wealth is in money, and 1 minus theta of all wealth is in capital or some other productive asset. So that's 1 minus theta. Okay. So in this world, if we want to value money, so figure out what is going to be the demand for money that people have. So instead of the risk-free asset, people trade and people hold money, and then the return on money. Okay, so for the risk-free rate, we've talked about what this is going to be, but for this world, the return on money in this numeraire world wealth. Okay, the return on money is going to be mu theta dt plus sigma theta dt, where those are some aggregate shocks. So basically, the money is in fixed supply, and we're interested in the value of money expressed in terms of the share of total wealth as the numeraire. Then this is just going to be the return on money. Okay. So money is different from other assets because it pays no dividends, right? Compare it to this equation, for example. So this is the return in this numeraire of the portfolio of agent I. So there is a dividend because agent I is consuming something, and there is some idiosyncratic risks. So but money has no idiosyncratic risk and no dividend. So it's just some coins or some seashells which people agree to trade. So this is the return on money. Okay. And this equation, okay, so if people, if everybody can hold the risk-free asset, this equation can be thought of as the equation that determines the risk-free rate. Okay, if everybody can trade money and the value of money is determined endogenously, then this same equation, so this is the return on money, it can be thought of as the equation, the money valuation equation. So let me just copy it there. C bar over n bar minus mu theta equals the sum over j, eta j sigma eta j minus sigma theta, because this is the volatility of money value, times Cj minus this is still sigma n bar. Sum over j j sigma tilde j squared. Okay? Let me write a specific form of this, for example, for logarithmic utility, which makes things easier. So imagine a world where utility is logarithmic, and let's say everybody has discount rate rho. Okay. So in that case, this is the world consumption rate minus, this is minus mu theta, and then this is sum over j, let's say eta j, this is sigma eta j minus sigma theta. In this part in parentheses for logarithmic utility, this is just going to be the volatility of wealth of agent type I. This is the volatility of world wealth, so the difference is the volatility of wealth share of agent type, well, not agent type I, agent type J, so it's just going to be that. And then plus the sum over J of eta J sigma J tilde squared. So this is the same thing I just wrote inside. And because and then I can simplify it. I can simplify this equation because the weighted average of wealth share volatilities with these weights equals 0, and they all multiply the same factor. So I can write it as rho minus mu theta equals the sum over eta over j, eta j sigma j sigma eta j squared plus the sum over j of eta j sigma j tilde squared okay, and then let me box it and let me interpret it. Okay. So in Buhle economies, people hold money because they're afraid of idiosyncratic risk exposure. Okay. And the right-hand side here is, well, not necessarily idiosyncratic, right? So it could be some, any type of risk, right? There. So basically, yeah. So the right-hand side here is basically the average risk exposure of everybody in the economy. And this is the discount rate, and this is the drift of the value of money. Okay. So if there's a lot of risk exposure on the right-hand side, so remember that you're thinking about an economy and it moves over the different states, and in some states it could be that basically the intermediary sector is hit, and maybe the intermediaries, they help households insure against the idiosyncratic risk. So there are states where there's going to be a lot of risk because the financial system is not working, and then there can be states where there's going to be less risk because the financial system is working smoothly. So basically, you can end up in different situations. So in states where you have a lot of risk, what this equation gives is that the right-hand side is large, So that means that mu theta is going to be a large negative number. So the value of money, the money falls in value, right? And what it means is that in states with a lot of risk, the value of money is going to be inflated, and it's going to be expected to basically to go down when situation normalizes. So those are the flight to safety states. So when there's flight to safety, then people go and they buy these safe assets, and these safe assets they rise in value, and they know that the safe assets their value will go down when the economy recovers, so that mu theta is negative. But despite that, there is still a lot of demand for the safe asset because there's a lot of risk exposure. Okay, and vice versa. In good states, when there is less risk, then the value of money is going to be lower, and then the return on money is going to be higher. So this is something that basically right away we can see from this formula. Okay. But let me use this formula to get something for a very, very simple economy. Okay, so let me give an example. So this example is basically a baseline model of money, and I'm getting here kind of in a strange way because I've talked about a general model of money, and from a general model of money. I go to the baseline model of money and usually do the other way around, but sometimes it's useful to do things different because it gives you slightly different perspective. So imagine that example. So it's an economy with one type of agent. So they can all hold this capital, and they produce the same output. They are identical agents. They choose investment. The only assumption I'm going to add is that this capital it's subject to idiosyncratic shocks. So there are these shocks, but they're idiosyncratic. So different agents, they have different shocks, and they cannot diversify them among themselves. So they have to hold them. So there are idiosyncratic shocks, sigma tilde, dz tilde. Okay. These agents, they're no aggregate shocks. They're only idiosyncratic shocks. And I want to ask the question: well, how much money will they hold? So this is an economy with only one type of agent. There are no different types of agents to talk about, like wealth shares. So there's no such thing as about wealth shares. So n equals 1, only one type of agent. Okay. And then what is that equation like? Well, so that equation becomes like this: rho minus mu theta equals. So this is the aggregate risk. Okay, we do not have this term, but idiosyncratic risk, we have idiosyncratic risk. And the idiosyncratic risk, how big is idiosyncratic risk? So people hold a portfolio of capital and money, and the portfolio weight on money is theta. The portfolio weight on capital is 1 minus theta, and therefore their idiosyncratic risk squared is 1 minus theta squared sigma tilde squared. Except, of course, we are at the steady, because wealth distribution is not changing, theta has to be constant. It's basically stationary equilibrium. So of course, we can look at various other equilibria because there are also equilibria. So okay, so in any model of money where money is intrinsically worthless, you know that there is an equilibrium. If it exists, there can be an equilibrium where money has value. But if there's an equilibrium where money has value, there's also always an equilibrium where money is worthless, and there are a bunch of equilibria, in between, right? So this equation, if I put this extra term, then it characterizes, the in-between equilibria as well. Okay, but let me not worry about the in-between equilibria. Then you only look at the stationary one. Then in the stationary equilibrium, basically, we have this equation. Okay, and this equation is basically has one unknown, theta, which is the portfolio weight on money. Okay, and this equation tells us that so there is an equilibrium in which money has value. Money equilibrium. If sigma tilde is bigger than square root of rho, okay, then you multiply sigma tilde squared by something which is less than 1, and you solve for theta in order to get rho. Okay, and then you also get that in this money equilibrium range, theta is increasing in sigma tilde. So basically you have that.